Hello everyone, this is Ghanem Sabih with the Process Engineering Tips channel. Today we're going to go over pressure drop calculation, which is really important for process engineers who works in the plant. You could use that for line sizing, you could use it also for pump sizing, and also troubleshooting for fouling. That's where you do the pressure drop calculation, and then you compare that to a reading for a pressure drop that you have, and then check if there is a fouling or not. So please share and subscribe for more content about process engineering tips. Thank you.
Here's a case study, which is said calculate the pressure drop in a 3-inch pipe. And in this pipe, there's cooling water at 30 degrees Celsius and volumetric flow rate of 150 gallon per minute. And use the following as metric. This like length of the pipe. And you have elevation, downward, upward. And you have fittings. You have 45 degree elbow, 90 degree elbow, drain, outlet, and entrance, temperature prob, a valve. So basically, what we need to do is we need to get all the info in one place, or set up our parameters. And I like all to set them at the same unit. And the unit I usually like is metric, and keep it at the simplest thing possible, which is basically, for pressure, Pascal, for mass, kilogram, for length, meter, and also for time second. So that would make everything easier, because a lot of the correlation we're going to use, they deal with unitless values. So you need to make everything at the same unit in order to avoid mistakes related to unit conversion. So I guess let's start by putting like density. Let's put density of water. It's say 995 kilogram per meter cube. And you could make sure, through a thermodynamic database or a property database, with the temperature. For densities for liquid, temperature doesn't matter this much, but viscosity is actually very important to make sure that you have the right viscosities at the right temperature. Because viscosities change a lot with temperature, and viscosity is really important because it's very hard to pump viscous material. Think about honey. Honey is a very viscous material. Imagine you pump like honey or Nutella or things like this, right? While water could be something that is easy to flow. So water usually is like 0.8 CP, which I think in metric is like 0.008 meter. Okay, so that's our density and viscosity. We will need something called the gravity constant. And that's like around 9.18. You could Google that. And then we have our volumetric flow rate. I'll call it Q, 150 gallon per minute. I think you could convert that. I like to convert it to cubic meter per second. And I think that would be equivalent to 0.00946, and that would be meter cube per second. And you have elevation. I think your elevation would be 20, but then you have a downward elevation, so you only need to get the difference between them. So 20 minus 2, that would be 18 foot, and that would be 5.4864 meter. I think for length, you could just sum those up, and that would be around 100 foot. Sum everything up would be around 100 foot. And I think that 100 foot would be equivalent to 30.48 meter. Another parameter we need to talk about is the diameter of the pipe. And this is 3-inch pipe, and this is a nominal diameter. So you need to know the internal diameter because every nominal every pipe has a thickness. Depend on its material and depend on schedule. And so based on that thickness, you could know basically what's the outer diameter and the internal diameter. The outer diameter is needed for if you're doing like a heat transfer calculation. Internal diameter would be good for a pressure drop calculation. You could Google like pipe schedule diameters, or sorry, pipe schedule charts, and you see like hundreds of websites. And so for a 3-inch nominal diameter, and say it's stainless steel schedule 40, you would get, an outer diameter of 3.5, internal diameter 3.068. As big or as high you go in the schedule, as more thickness or as more thick the pipe would be. So let's say D equal 3.068 inch, which is equivalent to 0.078 meter. Okay. Now let's talk a little bit about some equations. So the first thing we need to do is we need to talk about the Reynolds number, which is a dimensionless number that would tell us at which flow regime we are. And the flow regime is important because your pressure drop correlations are actually depend on the flow regime. So if you're like in a laminar flow, you're going to use a different equation to calculate pressure drop compared to like a turbulent flow. This is actually turbulent flow. Sorry about that. Okay. Now, so say for velocity, first to calculate the Reynolds number, you need the velocity and the diameter. And the velocity, we have a volumetric flow rate. But if you divide with the cross-sectional area, which is cross-sectional area for a pipe, would be this equation here, then you could get the volumetric flow rate, which is this, right? And that's what we got here, right? And then you have the diameter, which we just said 0.078. Okay, and this should give you, this should give you 1.98 meter per second. This is almost equivalent to 6 foot per second, which is actually really good. Because usually you need to see the velocity, because if the velocity is high in a pipe, let's say if it is higher than 10 feet per second, then you probably should change the pipe or upsize the pipe if you're designing a pipe, right? Because you're gonna have a lot of pressure drops as the velocity is high. 6 foot per second is reasonable. Usually you want to target somewhere between 4 to 10 feet per second if you want to size a pipe. Okay, so that's kind of rule of thumb. Okay. Now, if we put this here, so we have basically the diameter. So we have basically 995. This is actually the density, and the velocity is 1.98, and the diameter is 0.078, and the viscosity, as we said, it's basically 0.008, and actually that, and this should give us around like 192.158.7. So this is like 192,000 Reynolds number. So that would put us into the turbulent flow regime. Okay, so with that, we could select a correlation that's suitable for a turbulent flow. So to calculate the pressure drop, we need to account for all the sources of pressure drop. And there are 3 sources. There's the pressure drop due to friction, and also there's the one due to elevation, which is usually the dominant one. And also there's one due to fittings. So you could put the three equations together, and this one I think is equation from Darcy and Weisbach, and this is a function of the friction factor, which we will talk about how to get that. But everything else we know, and also for the fittings, this a function of something called KL, which is a coefficient for your fittings. So basically, you need to go to the isometric, and you need to get that coefficient for each fitting. So there's a coefficient for a valve, could be a ball valve, could be a gate valve. There's a coefficient for entrance and exit, also like drain, elbows, tees, things like this, right? And you could actually Google. There's a lot of website that will give you these coefficients for all kind of fittings. Okay, but I could teach you a trick. The trick is that that depend on the length of your pipe. Okay, you could use a factor, an equivalent length factor, and in that, if that's the case, then you actually don't need this. So if your pipe is from 50 feet to 150 feet, you could use a factor, and that factor is actually different for each diameter. So you could Google that factor, but for something like 3-inch, it would be like 2.3. So basically, if you have 100 feet pipe, you could assume that the pipe is 230 feet, and in this case, you don't need to account for the pressure drop in fitting because it should be already built in, and it's more conservative. And it does increase with the diameter. However, if the pipe length increases, I think up to 1,000 foot, well, it will reduce, but once you reach to, I think, like 1,000 feet, you actually don't need to account for that factor because the pressure drop to fitting would be negligent. So, and you don't need to worry about it. So for something like this, 100 foot, I'll use the 2.3 factor. So that would be 70.1 meter. Okay. And then, so we could put all the numbers here. This one we will delete, and the L, we would use the 70.1 meter. And we just need to find the friction factor. So the way to calculate friction factor, there is this equation. I think it was developed by Clobrook and White. So these two people came up with this equation. And this equation is suitable for tubular flow. Depending on your flow regime, the correlation would change. So that's why it's important to know which correlation to use. And the only issue with this equation is that you have the friction factor. It's in both sides of the equation. So in order to solve this, you need to do iteration. You could use Excel, and you could set the right-hand side of the equation minus the left-hand side equals 0. So you could use something like goal-seek. We could set 0 as the goal, and you change the friction factor. So Excel would run multiple iteration to give you the number that if you put here and there, they would equal each other. Okay, or you could just use a linearized equation. And a linearized equation is basically, as a lot of people came up with their own empirical equations a long time ago, because doing iteration was hard. Now it's easy with the tools we have. But why not? Let's use that. And the one I like to use is Moody correlation. And you got to be careful with this correlation because each correlation is suitable for a certain range of Reynolds number and also a certain range of roughness factor divided by diameter. Moody is good for a wide range of roughness factor of diameter and Reynolds numbers. Probably 80% of the time you could use that correlation. And roughness factor that's something you could Google. I mean, for steel would be like 0.00015 feet. So you need to convert that to meter in order to make the unit consistent. I just put it here. Okay. And so basically you have everything you need. So you have that number, you have the diameter, you have the round number. This would give you around 0.05547 if you plug everything and do it. So now we have all the parameters that we need to calculate the pressure drop. And as we said, this one we don't need because we use an equivalent length factor that would account for fittings. So now we could just basically plug these numbers in there, and you could do it in Excel, or you could do it in a calculator if you want to do it in paper and pen, which I usually like to do stuff in paper and pen. And so it's just a matter of plugging the numbers. This one, I think it was 1.98, and 5. And this is the height that the liquid will go to, which was the 18 foot. And that's like 5.4864 meters. And all this would give you somewhere around 63,283 Pascal. Now the Pascal you could convert to pounds, and I think it's like around 9 pounds. So you need like a pressure drop of 9 pounds. So that's basically what you are expecting in terms of the pressure drop. And let's say if you have the local gauges in point A and point B, and you see that the pressure drop is higher than that, that's mean you do have a fouling issue. So you could maybe clean the pipe. If you're sizing the pipe, or let's say if you're sizing, let's say if you're sizing a pump, so you need to see like the destination pressure. Let's say if it is the destination pressure is 15 pound. Okay, so to size the pump, you need the 15 pound plus the 9 pounds pressure drop, plus additional, a design cushion for your deadhead pressure. I usually like or recommend to use either 10% or 10% of that number, or you add 45 pound, whatever greatest here. Okay. And
I hope you enjoyed the video. I hope it was useful. If you have any question, I have my email in the bio. You could also comment on the video, and I'll reply as soon as possible. Thank you.